Wow, this brand new AAA title looks totally amazing. I have to play this. Science fiction, defending against asteroids in space. Exactly my kind of video game. This is gonna be so cool. Pew pew pew, yeah, I'll shoot down all the incoming rocks. Just like I did with the aliens and Space Invaders. Wait, what's that? Analog input device required to play? Oh no! I only have a keyboard and a mouse on my computer. There's no analog stick or trigger on it, just digital buttons. So I can't play Analog Asteroid Attack? Oh, but I must play this game. I have to come up with a solution. Looks like I have to build my own analog input device. I said I have to build my own analog input device. There's no way around that. And yes, I do have a mousepad with a gun-wielding cat riding a fire-breathing unicorn, because that is just awesome. Back to the topic. In this video I'd like to talk about analog and digital inputs as well as analog to digital conversion while building a very basic game controller similar to those of the first Pong consoles in the 1970s. While doing this, I will also give some additional explanation about electronic circuits, especially resistor combinations and voltage dividers. First of all, what's the difference between analog and digital? Well, quoting from Oxford Dictionary, analog, adjective, relating to or using signals or information represented by a continuously variable physical quantity. Digital, adjective, of signals or data, expressed as series of the digits 0 and 1. As you can see here on the standard gamepad, a simple button always has one of exactly two different states. It is either pushed down or not. This is what we refer to as a digital input because each button provides exactly one bit of information. In contrast to push buttons, analog stick or triggers provide a continuous value somewhere between a known minimum and a known maximum. Therefore, an analog trigger can, for example, be pushed down 25%, 90% or any other fraction. This obviously contains more information than a simple push button, so it's not just one bit. But in the end, we are still talking about digital computers, and these machines exclusively process zeros and ones. Keep in mind that these two digits are internally represented by two different voltages. A low voltage is interpreted as a 0 and a high voltage as a 1. So how do computers work with analog signals? The answer is very simple. Every continuously variable physical quantity such as brightness, pressure, temperature, acceleration and so on is first converted into a continuously variable voltage. This step is what a sensor does. Afterwards, this analog voltage is approximated by a sequence of low and high voltages representing a digital number whose value is proportional to the analog voltage. This translation process is called analog to digital conversion, or ADC for short. Before I can try to give you a rough idea of how that's done, I need to talk a bit about voltage dividers. Also, the analog input device I built relies on the concept of voltage division. So the first thing to understand when talking about voltage dividers is that when you put multiple resistors in a series, let's say like this, where you have one resistor with resistance R1, followed by a second resistor with resistance R2, then the overall resistance between these points is just the sum of R1 and R2. And that holds for an arbitrarily large number of resistors. So you can also put a lot of them in series like this, starting with R1, R2 until Rn, and the overall resistance of this entire thing is just the sum I from 1 to n over Ri. And while we're at that topic, what happens if you put resistors in parallel? So let's say we have one resistor R1 here and another one R2 here, and they are connected in parallel, so they are connected like this. Then what's the overall resistance between these 2 points? Let's call that X. Well, in this case, the resistance doesn't get higher, it actually gets lower. And to compute X, well, you just have to understand that in this case, the multiplicative inverse of R1 and R2 add up. So then what that means is that 1 divided by X equals 1 divided by R1 plus 1 divided by R2. So if we want to solve that for X, then we bring those fractions on the same denominator, meaning that 1 divided by X is R2 divided by R1 times R2 plus R1 divided by R1 times R2. So this is, whoops, that was wrong. R1 plus R2 divided by R1 times R2, and this is 1 divided by X, and of course this equation is equivalent to X equals R1 times R2 divided by R1 plus R2. So this is how you figure out the resistance of 2 resistors in parallel. And that also works for an arbitrarily large number of resistors. Time to verify some of that theory in an experiment. Here are 2 resistors in series. And the first one is a 100 kilo-ohm resistor with a measured value of about 98 kilo-ohm. And this is nothing special. There commonly are up to 1 or 2% tolerance in normal carbon film resistors, and for most applications that does not matter. For high-precision electronics there are better resistors available, but they are also more expensive. The second one is a 10 kilo-ohm resistor, and the overall resistance comes in at about 107.7 kilo-ohm. So the resistances did add up as expected. A voltage divider is nothing else than a couple of resistors in series between a supply voltage and ground. Remember, voltage is the difference in electric potential between 2 points, and ground is the reference point towards which all voltage measurements in a circuit are taken. A circuit like this splits up the supply voltage into smaller chunks, just like the overall resistance is split up into the individual resistors. In this case, the 9.21 volt are split up into 8.25 volt across the 98 kilo-ohm resistor and 0.96 volt across the 10 kilo-ohm resistor. Let's take a quick look at a few more examples. Whenever 2 identical resistors are used, the voltage is split in half. Generally, the voltage is split up in the same ratio as the overall resistance is split up. This can be verified via calculations according to the U equals R times I formula by first computing the overall current going through the circuit. Afterwards, one can apply the same formula with a now known current to solve for the voltage drop across each resistor. Now let's finally talk about the interesting part. How can this concept be used to realize an analog input device? Nothing simpler than that, by using a resistor with variable resistance. That's exactly what these control knobs and radio dials are, resistors that change their resistance depending on their current control state. These parts are called potentiometers. A voltage divider in which one of the resistors is a potentiometer can therefore be used as a sensor that translates physical motion, usually rotation, to an analog voltage. This analog voltage can then be sampled by an AD converter to get a number in digital representation. In my case, I use an ARM Cortex M4 microcontroller to handle the AD conversion and transmit the resulting numbers to my PC via a USB connection. The microcontroller itself is just this small chip here. The input-output pins of the controller are connected to these pins on the side of this STM32 discovery board that is made to simplify development and debugging for this microcontroller. There is a lot of other stuff on here as well, such as USB plugs, a programmer and debugger, quads, buttons, LEDs, a microphone, and so on. At the end of this video I will give a basic explanation of how analog to digital conversion can be realized in an electronic circuit, but first I will actually build the old school gamepad I've been talking about. While I'm doing this, let's go over the final circuit that is probably a lot simpler than you expect it to be. So, putting everything together, this is the final circuit for my gamepad. I already talked about the voltage dividers and the AD conversion here. The only new thing basically is the push button. And how does this work? Well, the PC2 input of the microcontroller is configured as a digital input with an internal pull-up resistor. What that means is that without any external interference, it will also always read a high voltage value, meaning a logical 1. So the circuit, what this does here is as soon as the button is pushed down, then the input is dragged down to ground, which means that the microcontroller will read a logical 0. And well, there's a 470 ohm resistor between the input and the push button, so it's technically not ground exactly because I basically built another voltage divider with the internal pull-up resistor and this 470 ohm resistor. But the 470 ohm are way smaller than the pull-up resistor, so it's not exactly ground the input will experience, but very close to it, and it will just read as a logical 0. So basically there's just one question remaining about this circuit. Why are there 470 ohm resistors at all? Technically you can just not use them. I tried it, it works, but it's just a precaution for safety reasons. Because what happens if you don't put in those two small 470 ohm resistors in this circuit? Well, then the inputs could have a direct connection to ground when the push button is down or when the variable resistor just has 0 resistance. And if the microcontroller is misconfigured, that could lead to this circuit just sinking an unlimited amount of current. And that's not really good for common microcontrollers. So it's just a precaution. The first thing I did was the preparation of the connection cable. I used a standard 10-wire ribbon cable and a pin connector having 2 rows of 5 pins each. This plug fits onto the pins of the STM Discovery board and covers all the pins the gamepad needs. While doing this, I measured continuity between the plug and the individual wires and carefully wrote down which wire color will connect to which pin. It's always a good idea to have a pen and a piece of paper available when improvising the circuit layout, as it can get somewhat confusing with all these small parts, wires and solder joints. To avoid lengthy debugging later, I also tried to test as many connections as possible immediately after soldering. Once the push button, the potentiometer and all of the resistors were put into place, I used the letters on the board to keep track of where to connect the wires. After soldering the wires to their corresponding connection points on the boards, I used my favorite DIY tool to add mechanical stability. The hot glue will make sure that the cable does not tear off of the board during exciting gameplay sessions. That's the entire hardware for my old school analog gamepad. Everything else is software on the microcontroller and on the computer. The software on the controller is very simple. The AD converter is just read in infinite loop, and after each conversion the digital input bit is set to an unused position of the 12-bit integer representing the analog value. Then the 2 bytes for this measurement are transmitted via a virtual COM port over the USB connection. That's not the most elegant way to do this, but by far the simplest one. Therefore the gamepad will not be recognized by any operating system as a game controller, but will only work with the demonstration software I wrote that opens a COM port and interprets the transmitted data correctly. Maybe I will build a real gamepad sometime in the future. The ARM Cortex I used is capable of presenting itself as a standard USB human interface device. And now it's time for the main event. Let's play Analog Asteroid Attack! The analog value from the potentiometer is used to control the Y position of the spaceship, the white circle. And the push button causes it to shoot white dots to the right. Although this is a very simple game, it's more fun to play than I thought it would be due to the unusual control scheme. Directly controlling the virtual position of the spaceship by turning the potentiometer left or right makes aiming and evading quite interesting. At least for a few minutes before my hand starts to hurt, as this gamepad is not really ergonomical. Potentiometers come in a variety of different shapes and sizes, and some of them are more suitable for a task like this than the one I used here. As mentioned, I'd like to conclude this video with a small insight into the internals of an ADC. Let me give you a rough idea how analog-digital conversion works. There are several approaches in practice to do this. One of the easiest ones to understand is using analog comparators. An analog comparator is a building part that, compares analog voltages. So it has two inputs, voltage VA and VB. That's supposed to be a B. And of course it also has a supply voltage and a ground reference. And this will output 1 bit of information. So the only output of an analog comparator is something that will read either a logical 1 corresponding to the supply voltage or a logical 0 corresponding to the ground. So what exactly will this output read? Well, it will read a 1 if VA is greater or equal to VB, or a 0 if that's not the case. Using a number of analog comparators, you can build an analog-digital conversion. And I'll show you on this diagram how this works. The digital number an ADC generates is always relative to a known reference voltage that has to be at least as high as the input voltage. In this example, I just set a ref to 16 volts. Utilizing a voltage divider with identical resistors, that voltage can be split up into smaller chunks, for example 4 volt each. These voltage ranges are just enumerated by the ADC. Here, any input voltage between 0 and 4 volt gets the number 0, 0, a voltage between 4 and 8 volt gets 0, 1, and so on. Analog comparison comes into play when deciding the individual bits of this output. The high bit B1 is 1 if and only if the input voltage is at least 8 volt. This can be decided by comparing the unknown input voltage to half the reference voltage. The next bit B2 can be set by comparing the input voltage to either 1/4 or 3/4 of the reference voltage depending on the first bit. Of course, this can be iterated for higher resolutions by adding more resistors to split the reference voltage into smaller chunks and using more comparators to get additional output bits. Actually, building this requires a bit more electronics than just the voltage divider and the comparators. But this concept is one simple way to digitize an unknown analog voltage. But of course, when you actually want to build something, I'd strongly recommend to do what I did. Just use a microcontroller for that task.
If you liked the video and you want to see more content like this, please consider supporting the channel by executing this algorithm. You will find all the necessary links down below in the description. Thanks for watching, have a nice day!